Picture a vast, frozen ocean, Arctic sea ice, meters thick and stretching endlessly to the horizon, a landscape so harsh and unforgiving that it seems almost alien. Here, temperatures plummet, winds howl, and the ice forms an unbroken barrier that few vessels dare to challenge. Now, imagine a ship, a steel giant, not avoiding the ice, but charging straight into it with unstoppable determination, its bow slicing forward where others would falter. This is the world of nuclear icebreakers, ships engineered for one brutal purpose: to smash through the frozen top of the world, conquering obstacles that would halt any ordinary vessel. A regular ship hitting ice risks disaster, trapped, immobilized, and at the mercy of the elements. But icebreakers are designed to do this all day, every day, for months on end, relentlessly pushing forward no matter how thick the ice becomes. They're the snowplows of the sea, carving vital paths for trade, scientific exploration, and emergency rescue through the Arctic's frozen expanse, opening up routes that would otherwise remain closed for most of the year. Their mission: keep crucial shipping lanes open, reach remote research sites that are otherwise inaccessible, and save lives when things go wrong in the coldest, most isolated places on Earth, where help is often days away. It's the classic unstoppable force versus immovable object, except here, the force must win every single time, or the consequences could be dire. To do that, you need more than just brute strength or courage. You need a vessel with immense, relentless power, a hull meticulously designed to exploit the weaknesses in the ice, shattering it with every advance, and the endurance to operate for months without port, supporting a crew in some of the harshest conditions on the planet. Conventional engines simply can't keep up with these demands, struggling and failing where the ice is thickest. For this job, you need something far more potent, an energy source that never quits, no matter how long or how far you travel. This is where you need to go nuclear, harnessing the power of the atom to break through the world's toughest ice. Welcome to the world of nuclear icebreakers, where human ingenuity meets the raw power of nature and prevails. Standard cargo ships are built for efficiency, not brute force. They're designed to move goods across vast oceans along predictable routes, where the biggest challenge is often just the weather or rough seas. But in the Arctic, the rules change completely. Icebreakers need colossal power on demand. Smashing through thick, multi-year ice is like driving through a brick wall, not cruising a highway. The ice can be meters thick, and only a ship with immense strength can push through. If you tried to use a regular diesel engine, you'd need millions of liters of fuel just to make a dent in the ice, making the ship incredibly heavy and drastically limiting its range. The more fuel you carry, the less space you have for supplies or crew. The heavier the ship, the deeper it sits in the water, which actually makes it harder to break ice. And as you burn fuel, your weight changes, affecting stability and performance. The Arctic is one of the most remote places on Earth. There are no convenient refueling stations, and missions can last for months, far from any port or civilization. Diesel ships would have to cut missions short or attempt risky refueling at sea, which is dangerous in freezing, unpredictable conditions. One mistake could leave a ship stranded in the ice. For the toughest ice breaking, diesel just doesn't cut it. Even the most powerful engines can stall or get trapped, leaving ships at the mercy of the elements. What you really need is a power source that's incredibly dense, able to generate huge amounts of energy from a small amount of fuel. Something that can keep going for years, not just weeks. It must fit inside a ship, yet propel a 30,000-ton vessel through solid ice, day after day, without stopping for fuel or repairs. The answer? A nuclear reactor. It's compact, powerful, and can run almost indefinitely compared to diesel. Russia, and before it the Soviet Union, solved this decades ago by putting nuclear power at sea. They pioneered the technology, building ships that could go where no others could. Nuclear icebreakers can run for years without refueling. That's the game changer that makes true Arctic exploration and shipping possible. How do you put a nuclear reactor on a ship? The principle is simple. Use nuclear fission to boil water. Inside the reactor, uranium atoms split, releasing heat in a controlled chain reaction. This heat boils water in a closed loop, creating high-pressure steam. The steam spins a turbine, which drives a generator, producing electricity. That electricity powers everything on board, from lights to massive electric motors that turn the propellers. The process: nuclear fission creates heat, heat makes steam, steam spins turbines, turbines generate electricity, and electricity drives the ship. It's a complex chain, but the result is nearly endless power. Unlike diesel, nuclear fuel lasts for years, not weeks. This floating power plant lets icebreakers operate deep in the Arctic, far from any port. It's the only way to keep moving through the world's toughest ice. Nuclear power isn't just an option, it's a necessity for true Arctic dominance. That's the secret behind these unstoppable ships. At the heart of a nuclear icebreaker, shielded by steel and concrete, sits the reactor, often two for redundancy. If one needs maintenance, the other keeps the ship running, a vital safety feature in the isolated Arctic. The reactor core is compact, housed in a thick steel vessel, circulating radioactive coolant in a sealed loop. Heat transfers to a secondary, non-radioactive loop, creating steam for the turbines. Control rods manage the chain reaction and, in emergencies, can shut down the reactor in seconds. Nuclear icebreakers can operate 5 to 7 years before refueling, compared to weeks for diesel ships. Refueling is rare and done only at specialized ports. The result? A ship that can break ice for years, limited only by food for the crew. That's endurance no conventional ship can match. Power alone isn't enough. The hull of an icebreaker is a marvel of design. The bow is rounded and sloped like a giant spoon to ride up onto the ice and crush it with the ship's weight. The process isn't ramming. It's using gravity to break the ice from above, then pushing the shattered pieces aside. The hull is incredibly thick, over 50 millimeters of special steel at the waterline, reinforced to survive constant punishment. Low-friction coatings and air or water lubrication systems help the ship slide through broken ice. Every element, from shape to structure, is optimized for one brutal task: crushing and clearing solid sea ice. It's less a ship, more a mobile ice-crushing platform. That's what it takes to conquer the Arctic. The propellers are the muscle, huge stainless steel or nickel aluminium bronze, built to survive a storm of ice chunks. Fixed pitch blades mean fewer moving parts, more reliability in freezing conditions. Nuclear electric propulsion allows precise, instant control, full ahead to full reverse in seconds. For thick ice, icebreakers use ramming: back up, charge forward, break the ice, repeat. The ability to reverse power instantly is essential to escape the ice's grip. The hull's shape protects the propellers from the worst impacts. Steering is a challenge. Rudders are reinforced, and some ships use azipods, rotating pods that can direct thrust in any direction. Azipods let the ship turn on the spot, move sideways, or even break ice going backwards. This gives the captain unmatched control in a dangerous, shifting environment. In the Arctic, maneuverability is survival. That's why every part of the propulsion system is built for power, precision, and resilience. It's brute force, perfectly controlled. Picture a convoy of cargo ships halted by Arctic ice. The ships sit motionless, surrounded by a frozen expanse that stretches as far as the eye can see, their hulls trapped in a world of white silence. On the distant horizon, a nuclear icebreaker appears. Its mission: to carve a path through hundreds of miles of frozen ocean where no ordinary vessel could hope to pass. The bow rides up onto the ice, then crashes down, cracking the frozen surface with thunderous force. In its wake, a channel of open water slowly emerges, a lifeline for the ships behind. Progress is slow and methodical. The captain, eyes fixed on radar screens and the shifting ice ahead, relies on years of experience to find the safest and most efficient route through the ever-changing maze. When faced with a massive pressure ridge, the ramming begins: back up, charge, shatter the ice, and repeat. Each attempt chips away at the obstacle, inching the convoy forward. This violent ballet can last for hours, powered by the ship's unwavering nuclear heart. Deep below deck, powerful reactors hum, providing the relentless energy needed to conquer the Arctic's toughest barriers. Life on board is a mix of routine and constant vibration, a self-contained town with all the essentials. Crew members find moments of rest, sharing meals and stories, while the ship's engines never sleep. The crew's mission: keep moving, keep the path open. Every member plays a vital role, from engineers to lookouts, ensuring the ship's progress through the frozen wilderness. Cargo ships follow closely, knowing the icebreaker is their only hope if the channel closes. Without its protection, they would be stranded, at the mercy of the Arctic's icy grip. In the vast frozen desert, the icebreaker is a lifeline, a steel island of warmth and power, forging ahead where nature seems unbeatable. Without it, the Arctic would remain impassable, a barrier to trade, exploration, and connection between distant lands. With it, the world's most extreme environment becomes a highway, opening new routes and possibilities for global commerce and discovery. That's the power of nuclear icebreakers, machines that turn the impossible into the everyday, conquering the Arctic 1 mile at a time. Why invest in these nuclear giants? Geography and economics. Melting ice is opening new shipping routes, like the Northern Sea route along Russia's coast, cutting travel time between Europe and Asia by up to 40%. But the Arctic isn't ice-free year-round. Powerful icebreakers are needed to keep these routes open and safe. Beyond trade, the Arctic holds vast reserves of oil, gas, and minerals, resources that require icebreakers to access and transport. Icebreakers also support polar research and project national presence in the region. Russia's investment in nuclear icebreakers is about trade, resources, science, and sovereignty. As the Arctic grows in importance, these ships are tools of economic and geopolitical power. They're more than ships, they're strategic assets. The future of icebreakers is bigger and more powerful. Russia's new Arktika-class ships are the largest ever, with variable draft for deep ocean and shallow rivers. Their RITM-200 reactors need refueling only once every 7 years. Just a few hundred kilograms of uranium over decades. Compare that to hundreds of thousands of tons of diesel for a conventional ship. The next leap, the lighter class, over 200 meters long, 70,000 tons, and 120 megawatts of power. It will break through 4-meter thick ice at speed, making year-round Arctic navigation possible for the largest ships. Nuclear icebreakers are a fusion of raw power, clever design, and cutting-edge technology. While other nations build powerful diesel ships, Russia's nuclear fleet leads the way. As the Arctic opens up, these ships will only grow in importance. They are, and will remain, the true kings of the frozen north.